we'll go ahead and get started here. Good morning. Okay, so hopefully you guys can read this problem. I'll read it out loud to you guys. So it says, Superman, shown in the figure below, weighs 200 pounds and pushes horizontally on the crate, as you can see here. If the coefficient of static friction between the 450-pound crate and the floor is mu c equals 0.3, and between Superman's boots and the floor is mu b is equal to 0.6, what would you expect to happen? And then, they give you a little hint here. They say, for example, the crate will move. If so, how, etc. And then it says, support your answer with free body diagrams and computations. So ultimately, we're looking at this situation here with Superman pushing on the box, and we need to think about the different things that could happen in this situation. It all depends on what friction is. If we take a big look at this situation, what we know is that between the crate and the ground here, we've got a coefficient of friction is equal to 0.3. And between his boots, we can say the coefficient is 0.6. And then some more knowns. We know that Superman is 200 pounds, which I'd assume he'd be more if he were made of steel, but okay. And then we've got the crate, which is 450 pounds, pushing down. And so those are basically the knowns that we have. We have dimensions on this crate. They don't give us dimensions on Superman, but that's because he's kind of in a variable position here. He can move. So ultimately, we need to think about what can happen. In this situation, there are about 3 things that can happen. The first thing, and probably the most obvious thing, is that this crate here will slide. So the friction under this crate will be end up being less than the force that he's putting on it, and it will end up sliding this way. So I'm going to write one case, which is crate slides. The next thing that we can see happening if we look at this crate is, since he's pushing at the very top of this crate, it could be likely that instead of it sliding, the crate will end up tipping and kind of falling over along this edge here. I'm going to go ahead and draw an arrow for that. And the second case here is that the crate tips. Now there's a third thing that can happen, and that would be Superman here is pushing on the crate, and he ends up sliding backwards. Morning. And so that's essentially a thing where he's pushing, his feet just keep sliding against the ground there. And those are the main 3 cases that we need to look at to solve for this. So essentially what the goal is now is we need to find out what this force of P is in all 3 of these situations. Because finding what this force P will kind of dictate which of these happens first. Because all of these cases here, the crate sliding, the crate tipping, and Superman sliding, they're all very likely to happen, but ultimately one of them is going to happen first. And that's going to be the only situation that will end up happening if it happens first. So we're going to go ahead and take a look at all these. We're going to start with case 1. And so for case 1, we said the crate slides. So what we want to do is take a look at this crate and see what exactly would be happening if it slides. And so we need to draw a free body diagram of it. So we'll have this box here. And then on this crate, the forces that are going to be acting on it, we're going to have P acting, let's just assume it's along the very top edge here. We're going to have the 450 pounds, which is going to be acting in the center. For this drawing, it doesn't quite matter so much as long as you have it pretty much centered where it would be. As far as up and down, it doesn't quite matter, but typically know that it would be acting in the very center of the object. And then that'll be 450 pounds. Next thing is, because the crate is staying in one position, it's not going up and down, we need to know that there's a normal force underneath it. I'll label it as NC. And then lastly, we need to know that there is a friction force. Now, if we have a P sliding this way, the crate is going to end up fighting against this P all the way up until it reaches basically a breaking point in its friction, where the friction can't go any higher, and then it just gives way. So first of all, though, we need to know that friction is going to be opposing motion. And so when we have this P force acting on the crate going to the left, the crate is going to want to move to the left. So we need to know that the friction on the crate, which I'll label as FC, is going to be moving to the right against that crate. It doesn't want the crate to move. And so that's what our free body diagram could look like. Dimensions aren't quite as important in this one, but I'm going to go ahead and put them in. And we've got 4 feet here. Okay, any questions about that so far? Okay, so what I was saying about friction is ultimately when the crate slides, friction is going to be at its maximum point. Well, we need to know that friction is always going to be less than or equal to normal force times mu. And that's a typical rule that, to be honest, I haven't watched your lecture videos, but if you guys have watched them, hopefully they've discussed this. But this is a typical rule that, let's say if P were a very small number, friction would be exactly equal to it, just because the crate wouldn't be moving. So as P would increase, friction would keep increasing and increasing up until it reaches that point. So that's why I say less than or equal to. Now, in the case of where the crate is sliding or just about to slide, then friction would end up being equal to the normal force, which I'm going to say NC, this normal force, times what they gave us, which is mu C. That's going to be friction C. And so when you write this out in the exam and whatnot, you're going to want to write something like at slip, because that lets the graders and other engineers know that what you're intending is that you know that friction is not always going to be this value, but you just know that when it reaches its maximum value, this is what it's going to be equal to. Does that make sense so far? Okay. So knowing this, what we need to do is we need to solve for this friction force, and then using this friction force, solve for P. Hi. So what we need to do first is we need to know what our normal force is, because we need normal force to solve for our friction force. So that's some of the forces in the Y. Hopefully you can see that we only have 2 forces in the Y, 450 going down and the normal force going up. So in this case, I'm just going to write it out as NC is equal to 450 pounds. And so using that, we can use what we know about friction. We can say that FC is equal to 450 pounds times mu C is equal to 0.3. And when we calculate that out, we should get 135 pounds. And that's our friction force. Now we're still not quite finished yet. We need to ultimately solve for what this P force is. And so we could do that by summing the forces in the X. Hopefully, again, you can see that there's only 2 forces in the X direction here. You have the friction force C going to the right and the pushing force going to the left. So I'm just going to, again, write out that this force, the pushing force, is going to end up equaling the friction force, which means that P is equal to 135 pounds. I'm going to draw a little box around it, just so we remember that later. Okay? I'm going to go ahead and move on to another case, if you guys are ready. And that second case, we labeled it earlier as case 2 up above, where the crate will tip. Now, ultimately, the crate will tip. It won't be the friction force giving out. It'll end up being the sum of the moments. And the moment caused by P here will be enough to overcome the rest of the moments in this crate and it will end up tipping. So this is where maybe a little bit of conceptual knowledge about what a crate would look like when it tips is going to come in handy. So I'm going to go ahead and draw the crate here. So known forces we have on it, again, are going to be our P force from Superman. We're going to have our 450 pounds right there in the middle. And this time it's really important. So we've got that. And then technically we do have still a friction force acting on it this way because in this case it's not slipping. So we're going to go ahead and label that FC. And then last but not least, we have the normal force. Now, this is where you need to kind of consider where exactly the normal force is acting. In this case over here where the crate is sliding, I just put it in the middle because it didn't really matter where the location of it was. All we needed to know about it was that it was acting upward to counteract the weight of the crate going downward. Well, in this case, not only is it counteracting the weight of the crate, but it's also going to be somewhere along this crate here in accordance to here. Well, what we need to know is that at tip, or at the very brink of tipping, when we have this pushing force going on this crate here, we need to know that this end over here on this crate is going to end up tilting upward a little bit. And so when this end ends up tilting upward, we're going to have a normal force acting right on the edge here. And so I'm trying to think of a good way to represent that. I guess if you look at this Clorox thing right here, that's where we did it earlier. If I were to push it over here, it just slides. It doesn't really matter where the normal force is acting. It's just going to slide. But as I get up into the top, if I were to push on the top like Superman is on the crate, I'm going to be pushing, and it's still sliding a little bit, but you can see that all the force going down on this is going to end up being transferred to this edge of the Clorox thing right here. Does that make sense? You're essentially creating a pivot point where all the force is going to be right there. And so that's what we're talking about with this crate here. Is this crate is going to end up kind of spinning around that way, around this pivot point, and all the normal force is going to be here. So here's where it's important that we do draw in dimensions. So what we need is we need to know that the normal force is acting on the edge here. We were given 2 feet up above in our picture here. So if we're given 2 feet, that means with our weight acting directly in the center, we're going to have 1 foot here and 1 foot here, with this going all the way up to the center there. The next thing we need to know about is the height here. So we're going to have 4 feet. So now we need to take a look at this whole system, and we need to solve for P. Well, this is where we need to take the moment about a point in this system, a particular point, to solve for P. Well, we've got a few. We could solve around the middle here, but if we did that, we'd have P and F and the normal force to solve for, so that's no good. We can't solve for anything if we went around the middle. Kind of similar deal if we went here at FC. We'd still have P and the normal force to solve for. So ultimately, the best point for us to solve the moments about is going to be this point right here on the outer edge, which we're going to label it as O. And so if we sum the moments about the point O, we're going to have 2 forces acting or causing a moment. We're going to have the 450 pounds going downward, and it's 1 foot away, and then we're going to have the pushing force going to the left at 4 feet away. This friction force here is acting along the bottom of this, which means it's acting in line with this point, and there's no distance along it. So there's not going to be any moment around here. It's just going to be pushing on it. So we're going to go ahead and solve the moments around O. So some of the moments about O is going to be equal to, first we can label our P force. It's going counterclockwise, so it's going to be positive times 4. And then our 450 pounds, it's going to end up going clockwise, so minus 450 times 1. And again, those are the only two forces causing a moment about that. So we're going to set it equal to 0. And so right at the point of tipping, P is going to end up being whatever satisfies this equation here, just as we discussed earlier. At the point of tipping, all of the normal force is going to be at this point here. And so if we go ahead and solve for P, we're going to get that P is 112.5 pounds. And again, I'll draw a little squiggly box. It kind of looks like, you guys remember the show Rugrats on Nickelodeon a long time ago? They had little boxes like that. I don't know. A little off topic. Anyway, so those are our first two cases here, the crate sliding and the crate tipping. But we have one more case, and that's Superman sliding on this crate. That's him trying with all his might to move the crate, but his boots start sliding out from under him. So I'm going to go ahead and draw the diagram for him. Now, the thing about Superman, and the reason why we're not saying he's going to tip, is they don't really give us a height of him. They don't give us any dimensions of Superman. So it's not logical for us to look at it and see, oh, he's going to have a moment force about a single point here, because we don't have any points about it. And if you really think about it, the way that he's positioned right here, he's really not going to tip. He's kind of firmly grounded in the ground, and if anything, he's just going to slide. So that's the case for this. Sometimes there might be another case where I don't know exactly what would be going on here, but maybe you have a rope between them, and they could be tipping or sliding if you have like two crates or something like that. But in this case here, we just have to worry about him slipping. And so we're going to draw a free body diagram of him. This is going to be kind of bad. I'm just going to draw a stick guy really badly. And so with our stick guy, we need to know the forces that are acting on him. So if we look back in our diagram, on Superman, we're obviously going to have our his weight going down. So I'm going to go ahead and draw his weight about halfway down where he is, of course, in the center, and draw an arrow along that, and that's going to be 200 pounds. By the way, don't feel the need to draw a stick person. Like if you just draw like a sphere or a box or something, that would do fine for it too. I just wanted to feel artsy today. So we've got the 200 pounds going down on it, and then also we've got his normal force, which I'm going to label as NS, normal force for Superman. And then last but not least, we've got this P force. So this is where we need to know our opposite and our equal and opposite reaction forces. If this P force is acting on this crate up here, that means that the crate is going to be enacting a P force on Superman up at the top. So I'm going to go ahead and draw a P going to the right on Superman, opposite of how he's pushing on the crate. It's kind of like that meme where it's like car salesman slaps the roof of car slaps car salesman back. If you guys haven't seen that, I might show it to you later on. But anyway, we've got the P force acting on Superman here. And last but not least, if he's not slipping, he's going to have a friction force, Fs, acting on him there. So these are all the forces that we need to know here, and we need to take a look at it as we did earlier. And so what we know above is that the friction force is going to be less than or equal to the normal force times mu. That's going to be this case here. But we need to say that at slip, Fs right here is going to be equal to, again, the normal force times mu b, which is the mu of his boots, which they give us up above here. And so again, this is saying that ultimately, up until the point where P gets too high that the friction can no longer hold it back, friction is going to be equal to this. This is the maximum that friction is going to be. And so we need to solve for, again, NS. We're going to sum for the forces in the Y. And summing for the forces in the Y, again, there's only two forces here. We've got the 200 pounds going down and NS going up. So NS is going to be equal to 200 pounds. And then using this, Fs is going to be equal to 200 times, and they gave us mu b as 0.6. And using this, we're going to calculate Fs is equal to, let's see here, should be 120 pounds. Okay, and then using what we know about Fs, we can go ahead and sum the forces in the x. Because ultimately, like I said earlier, we're solving for the p in all three of these cases. So sum of the forces in the x, again, we've got p going to the right, friction going to the left, and that's it. So p is going to end up being 120 pounds by itself. Okay, and we're still not done, because what the question is asking for is, what do you expect to happen? So in this situation, which of these cases is going to happen? Is the crate going to slide first? Is it going to tip first? Or is Superman going to start sliding as he's pushing? Well, this is where it comes in handy with the p's that we're solving for. Ultimately, all of these three things are dependent on how much p is acting on it. So we need to look at these situations. In the case of the crate sliding, in order for the crate to slide, p has to be a certain value. And the certain value to make it start sliding is this 135 pounds. Now, if we look at the case of it tipping, though, p needs to be significantly smaller for it to start tipping. So p is going to be 112.5 pounds to make that happen. And then similar for Superman is the minimum p we need for him to start slipping is 120 pounds. Well, ultimately, we need to solve for or find out what the smallest p value is, because that's going to happen first. If we look at this situation, the smallest p-value we have is this p-value right here, the 112.5 pounds. So 112.5 pounds. Ultimately, this means that the first thing that's going to happen is the crate is going to tip. And once the crate starts tipping, none of these other things particularly matter, just because the crate is already starting to do that. So we've reached a value of p that causes it to tip first, before Superman has a chance to slide or before the crate has a chance to slide. So we can say this, our p-value, and we can say the crate will tip. Does that make sense to you guys? All right, does anybody have any questions about that? Yeah, what's up?
Would there ever be a situation where it's like they neither move?
Where neither one moves? I'm trying to think. I feel like most of these are kind of solving for what's going to happen first. A lot of them are kind of in this format where you're going to solve for what the p-values are. I think there might be a case where they'll give you a value for p. So let's say they gave us that p is equal to, let's say, 100 or something. And they say, hey, what is going to happen if p equals 100? And then you'd go through and solve for each of these as we did. And in this case, all of our p's are greater than 100. So if these are greater than the 100 that they gave us, you would say neither of them moves, nothing really happens. So does that answer your question? Okay. Any other questions about this? Okay. We'll go ahead. I've got one more for you guys that will, I think that's all that you guys are really doing in lecture this week, or at least I've already looked at. So this is actually from my exam when I took the class. So the question is, the small block B rests on top of the large block A. The coefficients of static friction are shown in the figure, with mu B being 0.3, mu A being 0.2. Determine the smallest value of applied P force that will cause block B to move to the right. So ultimately, we want to see what will cause this to start sliding. And so this is where we need to look at our free body diagrams, but we also need to think about just exactly what is going to be happening in this case. And so if we take a look at this diagram here, we can see that these two blocks, B is on top of A, there's a P force acting on B, and there's a pulley with a rope between them. So that means that as B, if B is moving to the right, that means that A is going to have to be moving to the left in order for it to move. And then to complicate things even more, there's friction forces between both of these that we need to take into account. So this is where free body diagrams are very helpful and very necessary for these types of things. So I'm going to go ahead and start with the free body diagram of block B. I'm starting with block B because it's on top and it just looks more simple to deal with than block A, which has a few more factors acting on it. So if we draw out block B, we're going to have a block, something like this. We can look at the forces on it. So first thing that you should notice is probably that P is acting to the right. And then we've also got, it's 10 kilograms, we've got the weight acting down on it, which I will label as 98.1 newtons. And then in addition, we've got the tension force of the rope going to the left now. And with ropes, again, in case you've forgotten, you always assume them to be in tension because ropes really can't be in compression, because you can't really push on a rope and expect anything to happen. So we've got the tension force pulling on it to the left. And then next, we've got the friction force. Now, the friction force might be kind of difficult to look at, but again, we just need to know that friction force is always going to be opposite of the motion, or the motion that wants to happen. So in the case here, what we're solving for is the applied force P that will cause the block to move to the right. So if the block is moving to the right, that means that we're going to have a friction force acting to the left. And I'm going to label this friction force as FB. And then last but not least, we also have the moment force, the normal force acting upward. And in this case here, we're not solving for either of them tipping. They're both a lot wider than they are tall. And in that case, there's really not tipping going to happen, especially since the tension forces and the P force are all kind of acting in the middle of these blocks. We really don't have to anticipate any tipping in this case. Tipping ultimately, if I go back to this problem, matters most if the height is probably significantly taller than the base. Not to say that it couldn't happen if it was a square, it very well could. But if it's something where if the crate were on its side, we wouldn't really have to worry too much about it tipping, because it's going to start sliding first, because the moment forces are going to end up being really large to make it tip. So anyway, this is our block B with all of our forces acting on that. Next, we can draw the free body diagram for our block A. And so for block A, what we've got acting on it, we can go ahead and draw the rectangle here. On the rectangle here, we are going to have the tension force again acting to the left here where the rope is attached. We're going to have the force of its weight acting downward. So it's going to be 60 kilograms times 9.81, which I'll go ahead right in here. And I calculated that as, let's see here. Looks like I didn't calculate that earlier. So I'm just going to write it as 60 times 9.81. And then we need to take a look at what's happening here. This is where it gets maybe a little bit more conceptual, and maybe a little more complicated. We need to think about that if B is moving to the right, as the question is asking us, when B is moving to the right, the motion is going to go through the rope and around the pulley. So if B is moving to the right, we know that A has to be moving to the left, just because this rope is going to end up pushing on it toward the left. And so if A is moving to the left, we're going to have a friction force, FA, going to the right. And then there's some other forces here that are also tricky for you to see if you're not really taking a deep look at this and thinking about it. So, of course, acting upward to counteract this force is going to be a normal force, A. But that's not the only normal force that we need to worry about. This is again a case where equal and opposite reaction forces comes into play. Because if we look back at block B, we have the normal force of block B acting upward. But in our diagram, we see that the normal force would be acting somewhere along that point there. So that means as the normal force B is acting upward, equal and opposite reaction forces tells us that normal force B is also going to be acting downward. So I'm going to go ahead and draw or write in NB in an arrow acting downward on this shape. And that's something that you need to be careful of, and you need to make sure that you're looking in it. So it always is helpful to look at both of your free body diagrams and make sure that if there's some force acting upward on this, some normal force, make sure that you have where it's acting down here. And then last but not least, also is the friction force. Because not only does A have a friction force between itself and the ground, but it also has a friction force between itself and B here. And so as they're moving, there's going to be a friction force here. Now conceptually, this is really hard to look at by itself. I honestly couldn't tell you exactly which direction friction would be acting on A by itself. And that's where the free body diagram of block B is going to come in handy. Because in block B, we drew it to oppose the motion to the right, meaning that friction went to the left. Well, again, our equal and opposite reaction forces tells us that FB is going to be acting to the right, opposite of what it is acting on force B. And those should be all of the forces that would be acting on block A. And so now this is where we get into our equilibrium equations. But again, first thing that we need to know is that we need to know that friction is, again, less than or equal to the normal force times mu. And so that will account for two different situations of friction here. So we're going to take a look at block B first because there's less unknowns to solve for than in block A, and quite a few of the unknowns in block A are in block B. So starting at block B here, we need to take a look here, and we need to know that if it were slipping, the friction force B would end up being equal to the normal force B times whatever the coefficient of friction is. So we need to write, again, at slip, FB is going to be equal to NB times, getting a phone call, NB times, what did they give us here? 0.3 is what they gave us there. Or NB times mu B for now. Well, I'm going to go ahead and write 4B at slip. Solving for NB in this, we're going to take the sum of the forces in the y. We're going to end up having NB minus 98.1, which ends up giving us, and that's equal to 0, NB is equal to 98.1. So therefore, the friction force B is equal to 98.1 times 0.3. If we calculate that out, we end up getting 29.43 newtons. And that is our friction force for B. We can go ahead and use that down below at A. So next, what we need to solve for is, if we were to look at this, we ultimately need to solve for what this P force is here. Well, we can't solve for that right now without this tension force. So we are going to have to find out what this tension force is. In order to find out what this tension force is, we're going to have to take a look at block A. So for block A at slip, it's going to be a similar deal. So for A at slip, we need to know that FA is going to be equal to NA times mu A. And this is where we need to do, again, summing the forces in the y. And if we were to sum the forces in the y, we'd have NA acting upward minus 60 times 98.1 minus NB is equal to 0, because the normal force of B is now playing a role into our sum of forces here. And so NA is going to be equal to 60 times 98.1 plus, we found NB to be 98.1. So NA is going to be equal to, looks like 686.7 newtons. So using this information here, we can say that FA is equal to 686.7 times mu A they gave us up here again as 0.2. And so FA is therefore going to be equal to 137.34 newtons. Okay, and now looking at this free body diagram of block A, we have FA and we have FB. Now we need to just solve for T right here, and then we can use this T to help us solve for P. So we're going to go ahead and sum the forces in the X. And this is again for A. So sum of the forces in the X, we're going to have FB plus FA minus T, and that's equal to 0. So we're essentially going to have T is equal to FB, which is 29.43, plus FA, which is 137.34, which makes T equal to 166.77 newtons. And then last but not least, finally we can do the sum of the forces in the X on block B, because we know both of these unknowns down here, the tension and the force of friction in B. So for B, we're going to go ahead and sum the forces in the X, and we've got P acting to the right, so a positive P minus T minus force of friction B, because these are going to the left. And those are the only three forces that are going to be acting in the X, so we can set that equal to 0, and P is going to be equal to the tension plus the friction, because it needs to overcome those. And we have 166.77 plus 1, what do they get for that? Plus 29.43. And that means P is going to be equal to 196.2 newtons. And that is what we need to know for that problem, because it was asking for the smallest value of P that will cause it to move to the right. Well, ultimately, in this case, because it can't tip or anything, that's the only value of P that we need to look for. There's really only one case to look for. If these were any taller, and if I'm going to draw a quick sketch right here. If B, for whatever reason, were super tall, and we had P acting on it there, then you would want to consider a case where it would be tipping. And then you'd have to look at which of those P's would be smaller. But for this case here, there's only one case for us to look at, and that's if both of these blocks are just slipping. Does anybody have any questions about that problem? Okay. Those are the only two problems that I had for you guys today.